Well, hello there. This is Craig Hane or Dr. Dell, and this video is about a Riemannian geometry problem in the plane that we live on, which is the surface of the Earth, and I call it 1 mile south, 1 mile east, 1 mile north. Suppose those are the instructions that you're given to follow. And I want to remind you, first of all, that on the surface of the Earth, directions are measured by longitude lines for north and south. These are great circles. Now, a great circle is a circle that whose center, it's on the surface of the Earth, and whose center is the center of the Earth. And we're going to think of the Earth as a perfect sphere for this discussion. We always idealize things in math with math models. And so that's what a longitude line is. Go from North Pole to South Pole, and it's a great circle. Now, latitude lines are something different. The equator, which is perpendicular to the longitude lines, is a great circle right then at the center between the North and the South Pole. The latitude lines are actually lines that are not great circles. They're on planes that are parallel to the plane that the equator creates. So get a globe if you need to and look at that and understand it. Now, a latitude line, therefore, is not what would be called a straight line because it's not the shortest distance. The shortest distance between any 2 points on Earth is determined by the length of the line segment of the great circle that's determined by these 2 points. Okay, so if you have 2 points on a latitude line that are due east and west from each other, and if you go to them on the latitude line, you're not going the shortest distance, and every navigator knows that. But if you're told to go 1 mile due east, that means on a latitude line. So for the purpose of this discussion, we don't really care about shortest distances. We care about going on longitude lines and latitude lines. So when I say to go 1 mile due east, I mean on a latitude line. Now the truth is, when you get there, you're going to actually be a little bit less than a mile away because you didn't take the shortest distance, but we don't care about that. And like I said, I suggest that you get yourself just a ball even, and just start playing with it and looking at it and marking on it and so on. Now you've got to understand what I just told you to understand what we're about to talk about. Longitude and latitude lines. Most children learn these in elementary school with a globe, but if not, you want to make sure you learn it. Remember, this video is for high school students. This video is aimed at high school students. And it's like a lot of my other videos, it's about things that I wish I'd been taught when I was really young, and I didn't learn them until much later in life. Okay, here we go. Pick a point on the surface of the Earth, and we're going to call that point A. And I'm saying near Chicago, Illinois. In other words, more or less halfway between the North Pole and the equator, somewhere in that area. Call it A. Now here's the instructions. I want you to go 1 mile due south along a longitude line to a point, we'll call it B. Then I want you to go 1 mile due east along a latitude line to a point, we're going to call it C. Then I want you to go 1 mile due north along a longitude line to a point we'll call D. Now the question is, where is D compared to A, which is where you started? Now some people would say, well, you're 1 mile due east of A, and that would be wrong. Now A and D will be on the same latitude line because when you went north and south, you did along longitude lines. So you started on the latitude line, went a mile south, went east, went back a mile north, and you're on the same latitude line. But here's the point you got to realize. The latitude line that goes through the points A and D has a smaller circumference than the latitude line that goes through B and C. Get a globe and look at that if you need to see that. In other words, as you go towards the North Pole, the latitude lines get smaller and smaller in circumference. So when you end back up at D, you're actually a little bit less than a mile east of A on that latitude line. Now, as you go up towards the North Pole with the point A, then the distances between A and D are going to get shorter and shorter as you get nearer the pole. And in fact, what happens if A is actually on the North Pole? You go a mile south, a mile east, a mile north, and what happens? Whoop, you end up right where you started. D and A are the same. So if you go back to my video that I did for you on the Pythagorean theorem, was it always true or not? Near the end of the video, I asked you some questions. And one question was, could you ever find a place on Earth where you went a mile south, east, and north, and ended up right where you started? And indeed, how many such places are there? And the answer now we know, well, it's at least one, the North Pole. Now you can go around the northern hemisphere, which is the half of the Earth that's above the equator, between the equator and the North Pole, and look, and I do not believe you'll find any other points where that'll happen. In fact, I'm quite confident you will not. And so we'll say that the answer is 0 as far as we know so far. Now, of course, what about the southern hemisphere? Now, I pointed out in the notes that if you go from the equator to the North Pole, the latitude lines get smaller and smaller in circumference. And if you go south from the equator towards the South Pole, again, the latitude line gets smaller and smaller. So now the question that I'm going to ask you is there any place on Earth you can put the point where the answer is going to end up being D is exactly 1 mile east of A? Now I want you to stop and think about that. You should be able to answer this at this point in time without me telling you. I will tell you the answer is yes. So at least you know. And a lot of times, by the way, in math, if someone tells you, yes, there is such a point, then it gives you the confidence to go look for it. If you didn't know if there's such a point, you might not even go looking. By the way, that's a real problem in math. A lot of times people just don't look because they just don't believe it exists. Well, here's a question. Could it be on the equator? Well, think about it. The answer is no. If you go a mile south and then come back up, the distance between A and D and then east and north is going to be greater. Why? Well, when you went south, the latitude line where you landed for B has less circumference. You go a mile east on it. Then when you come back up, you're going to a bigger latitude line. So actually now, the distance between A and D is going to be greater than 1 mile east. So the equator is not the answer. So stop and think about it. Well, I hope you got this as an answer. It's the only answer I know of, and I think it's the only one, and it works. Start 1/2 mile north of the equator. Think about that. Now, when you go a mile south, where are you going to end up? B is going to be a 1/2 mile south of the equator. Well, the latitude lines that are 1/2 mile north of the equator and a 1/2 mile south are the same length. So when you go east to C and then back up north, back up to D, you're going to be exactly 1 mile east because those two latitude lines had the same length. Any latitude line in the northern hemisphere has a corresponding one in the southern hemisphere of the same length. Don't you see the symmetry? There's symmetry involved here. Now the question is, what happens as you go further and further towards the South Pole? Well, I'll let you trace that out and think what you think about. And then the question is there any place in the southern hemisphere where you could end up exactly where you started, where A and D would be the same? Now, a lot of people start around and say, well, let's try the South Pole. The North Pole work? Well, no, the South Pole won't work. Why not? Well, when you're at the South Pole, there's only one direction you can go, and that's north. So you can't follow the directions. In fact, here's a question I didn't ask. Are there any places on Earth where you cannot follow these directions? And the answer, of course, is yeah, there's an infinite number of places. If A is closer than a mile from the South Pole, you can't follow the directions. Why? As soon as you get to the South Pole, you can't go. The only way you can go is north. You can't go east. So there's actually an infinite number of points where you cannot even follow these directions. I didn't ask that question. And by the way, if you're making up riddles to stump people with, that's a good one. Here's the directions. You go a mile south, a mile east, a mile north. Are there any places on Earth where you can't do that? Where you just simply can't do that? And the answer is yeah. If you're within a mile of the South Pole, you can't do it. Now, at this point in time, if you stop and think about it, you ought to be able to figure out. I'm going to give you a hint. If you can find a place where A and D will end up being the same, there's going to be an infinite number of places in the southern hemisphere. And here's the answer. Around the South Pole, find a latitude line whose circumference is exactly a mile. You can do that. Pick a point A now that is 1 mile north of this latitude line. You go south, you go east, you go all the way around the latitude line, end up, so B and C are the same point. Now you go back north, and you get D, and you hit A, so A and D are the same. Now any point on a latitude line that's a mile north of this latitude line is going to work. So there's an infinite number of points where you can do that, an infinite number of points. Are there any other points? And the answer is yes, there's an infinity of infinity points. Let me show you how that works. Take a latitude line around the South Pole that's 1 over n miles long. N is an integer. It could be 2, 3, 4, 5, 6, anything. Let's say it's 1 over n. Now you take a latitude line. I misspelled that. A latitude line in the notes. A latitude line 1 mile north of this given latitude line. Now you start on this latitude line is a mile north. You go down to this one, and you go around it, go east n times. That'll be a mile, because n times 1 over n is a mile. And then B, you end up right where you started at B, go back north, you hit A. And n can be any natural number. So there's an infinite number of latitude lines where this will work. So there's an infinity of infinities. If you go watch my video on infinities, you'll see that. And that's really quite interesting. So this was what I wanted to tell you. It's in mathematics, you have a lot of interesting things you create with your axiomatic systems. And in this case, the surface of the Earth is a geometry. It's a plane. It has curvature. So it's what we would call, it's a non-Euclidean geometry. There are no parallel lines. On the surface of the Earth, any two great circles intersect. And the only straight lines are great circles. If you define a straight line as between any 2 points on it's the shortest distance, then the great circles are the straight lines. There are no straight lines in the sense of Euclidean, like on a blackboard. The straight lines are great circles, and they all intersect. So there is no parallel postulate. You can't say, given a straight line and an external point, there's a straight line parallel through that point to the given line. You can't say that. The parallel postulate is not true. So it's not Euclidean. This is not a non-Euclidean geometry. And when you have a non-Euclidean geometry, as I pointed out to you, the Pythagorean theorem is not true, for example. But then also you get other anomalies like this. If you're used to living in the Euclidean world, and you think in the Euclidean world, if someone tells you go a mile south, a mile east, a mile north, you're going to say, oh, I'll end up a mile east. And by the way, on the surface of the Earth, the mile is not very long, so that it'll be just slightly shorter than a mile. Nothing you can measure probably with any reasonable instrument. But what if I said 1,000 miles? You go 1,000 miles south, 1,000 miles east, 1,000 miles north. Now the difference will be measurable. You can figure it out using trigonometry. If you wanted to know, it wouldn't be too hard to figure out with trigonometry. In fact, that might be a nice problem for you. Start at a point in, say, Chicago, go 1,000 miles and 1,000 miles east and 1,000 miles north, and then measure how far east you are, and it'll be significantly less. I don't know the answer, I haven't done it, but it can be easily done, well, pretty easily done with trigonometry. All you need is trigonometry, I believe. And of course, the area of knowing the circumference of a circle and some things of that nature. Now, you might have heard, for example, that there are places on Earth where if you want to fly due east, you fly over the North Pole to get there. Well, if you take a latitude line up near the North Pole, and you want to go from a point on one side of it to the point on the other, a lot of times the shortest distance is the great circle over the North Pole, not going due east on the latitude line. Now, you've probably heard of that. Well, that's what this is all about. So if you're going to be a navigator and you're going to do things on the surface of the Earth, you got to learn this non-Euclidean geometry. Okay, well, this is just food for thought for a high school student. These are things that I wish that I had been taught when I was a young child, a young boy. I didn't learn a lot of these things so much later in life, back the education system we had then, and you're learning it now. So this is Dr. Dell. I will see you on another video.